Hi, this is a video about limits at infinity that relates to James Stewart's calculus textbook, chapter 4, section 4. Limits at infinity. So let's get going. So when we say something like the limit as x approaches infinity of some functions equals L, where L is a limit, what are we saying? We're saying that the bigger that we make x, the closer it gets to some limit. Usually you're going to have some kind of a horizontal asymptote here. It never quite gets to that line, but it gets as x gets bigger and bigger and bigger and bigger and bigger and bigger, x gets closer, f of x gets closer and closer and closer to that limit, but it never reaches it. That you could go on forever and ever and ever and ever as x gets bigger and bigger and bigger and bigger, but you would never quite reach that number, whatever it is, that y equals 1 or y equals 5. You'd never quite reach it. And that's what we call a limit. The limit as x approaches infinity of f of x of some functions approaches L, some number. That's called a limit as x approaches infinity. I think there's a tendency to overthink these things. If you look at the graphs, for example, in the calculus textbook I'm using, if you look at the graph, it's just pretty easy to see in the graph that, again, that x just gets closer and closer to something, to this imaginary line we call an asymptote, but it never quite gets there. That's what a limit is. So we could do the same thing with negative infinity. So we could say that the limit as x approaches negative infinity, whatever the graph is, that the limit as x approaches negative infinity, the smaller and 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 smaller that x gets, it never quite gets to this number, which we call the limit. So the limit as x approaches negative infinity of some function equals a limit, equals L. Again, we're saying that the smaller we make x, the closer it gets to L, but it never actually reaches L. So that's a limit. Some key points. Infinity is not a number. What you'll find is that mathematicians make these distinctions that to most of us it's like, I don't quite get it, but it's important for the rigor of the theory of the math. So infinity is not a number. Infinity just means you never stop. It's not, you don't, I've reached infinity. You never reach infinity. It just keeps going. And again, as I've said, limits at some of these L's are horizontal asymptotes, which means there's an imaginary line there that it never quite reaches. Okay, so here's a theorem that is demonstrated in the particular section I'm looking at. So let's say that r is greater than 0 is a rational number. A rational number, again, is a number divided. It can be put in the form of a number divided by a number. If the bottom can be 1, so this includes integers and whole numbers and all those other good things. So let's say that r is greater than 0 is a rational number. Then the limit as x approaches infinity of 1 over x to the r equals 0. This makes sense because the bigger the bottom part gets, the bigger and bigger the bottom part gets, the smaller and smaller 1 over that number gets. And so you have 1 over 10, 1 over 100, 1 over 1,000, 1 over a million, 1 over a quadrillion, 1 over a septillion, and 1 over a Google. The bigger you get, the smaller this limit gets. And so we say that the limit as x approaches infinity of 1 over x to any power, could be x to the 1, which would be 1 over x. That's going to, as x gets bigger, this goes to 0. By the way, not any power. Can't be r to the 0 because that would be 1 over 1, which would be 1. But if r is greater than 0, the limit of this is going to be 0. So that's a theorem. It's worth just, if it doesn't make sense to you, just remember that if you're taking the limit as x approaches infinity of 1 over x, then it's gonna go to 0. So with that in mind, let's look at this example. What is the limit as x approaches infinity of this polynomial on the top divided by this polynomial on the bottom? What is it? Well, how do you solve something like this? Your first impression might be, well, x squared and x's go to infinity, and so it's going to be infinity over infinity. Here's where the mathematicians say infinity is not a number, because normally you'd say with any other number, something over something equals 1. So you might think, well, infinity over infinity is 1. But infinity is not a number, so that doesn't work. These are deceiving because it looks like, it looks like infinity over infinity. What do I do with that? And you don't know what to do with that. But the way to handle this is you're going to divide both the numerator and the denominator by the highest degree of the denominator. So the highest degree of the denominator is 2. It's x squared in the bottom. It happens to be x squared in the numerator too, but that's not important right now. And so we're going to divide the top part by x squared, and we're going to divide the bottom part by x squared. Well, to save typing, I went ahead and filled in some of the steps. You should be able to do some of this in your head. So if you divide 5x squared by x squared, you get 5. If you divide 6x squared by x squared, you get 6. And then all the signs are the same. If you divide 2x by x squared, you get 2 over x. If you divide 1 by x squared, you get 1 over x squared. If you divide 3x by x squared, you get 3 over x. If you divide 7 by x, so you see how it goes. Now, given the theorem we just had, that any number over x to any power, the limit as x approaches infinity is 0, then what we're going to see is that 2 over x, the limit as x approaches infinity of that, goes to 0. Womp womp. Limit of this, as x approaches infinity, goes to 0. Womp womp. Limit of this, womp womp. Limit of this, womp womp. And so we're left with 5/6. Now you would have never gotten that from just looking at this, but by doing a little trick, we find out that the limit as x approaches infinity of this polynomial divided by this polynomial equals 5/6. Okay, so infinite limits. Now this means that as x becomes larger and larger, then f of x gets larger and larger without approaching a specific number. This is the one where it actually does go to infinity as x goes to infinity. So there's no horizontal asymptote involved in this kind of an infinite limit. So this is the kind of situation where the limit as x approaches infinity of some function is actually infinity. They both just get bigger and bigger and bigger and bigger. So the limit laws don't apply in this case because infinity is not a number. Yay, mathematicians and their fine points. Okay, so now the chapter ends with a precise definition. Again, don't overthink this. This really is very easy. It seems very hard, but it's actually very easy. And frankly, you don't need to know this to do calculus. Certainly not in any practical sense. We're getting into the stuff of the mathematical theoreticians. These are the if you think math is abstract, these are the abstract math people to end all abstract math. So these have to do with the precise definitions of a limit. Boy, that looks confusing. In fact, I had my calculus professor in high school called this the epsilon, this sort of stuff. He called the epsilon delta confusion. He claimed that he never knew anybody who understood it except for a fellow who always fell down the stairs at the Florida State University in Tallahassee. I don't believe him. I actually think it's fairly easy to understand this sort of stuff. What gets you is it seems like what? Seems like this is ridiculous. Why do I need to know this? This is the legal. You know how you click I accept the terms, and you don't. Most people don't read the 20 pages of. If under this circumstance, this happens and this happens. Most people don't read the fine print of contracts, when you're getting an app or something like that. This is the fine print of calculus. You'll do just fine with any calculus application without paying any attention to it. But these are some precise definitions, and since they're here and you may have a professor who wants you to know it, or maybe you're a math major, let me just explain what this is all about. So basically, what we're saying is that we're creating this concept called an epsilon. You can think of it as an E, but I think it's an epsilon. For every epsilon that is greater than 0, there is a corresponding number n such that if x is greater than n, then f of x minus L is less than E. E basically is a number that we can make it as small as we like, and we're still going to be able to get smaller. it's basically saying that we never actually get to the limit. That there's always going to be some difference. There's always going to be some difference E between the limit and where we are in x. That no matter how high we go with the x, there's always going to be a little gap between that and the limit. That if we take the function and we subtract, if we take the function and we subtract the limit, and take the absolute value of that, there's always going to be a little gap, and we're calling that little gap epsilon. There's always going to be a little gap between where the function is and where the limit is. And we can make x as big as we want, and no matter how far we go, because we're going to infinity, right? X approaches infinity. That no matter how big we make x, there's always going to be a little epsilon, there's always going to be a little gap between the function and the limit. Okay, same thing, this is the negative version. Basically, the limit as x approaches negative infinity. Means that we're going to be able to find, no matter how arbitrarily small we make epsilon, we're going to be able to find a more negative number that gets even closer to the limit. And then finally, precise definitions 3 has to do with, I think this should be the limit as it approaches infinity. So this is wrong. Sorry, it shouldn't be L, capital L. It shouldn't be capital L. It should be infinity on the right side of the screen there. That we're always going to be able to find another number that's bigger, is what it's saying. These are just basically very precise ways of saying what is pretty much common sense, I would say. So there you have it. Infinite limits.